Here's a question a child can answer. How many R's are in raspberry? Ask the language model running on this machine. Llama 3.1, 8 billion parameters, no randomness. And it says 2. There are 3. It gets strawberry right. Now almost every model does, because the internet spent a year laughing about strawberry and the models read the internet. But raspberry? 2. Blueberry? 3. This isn't a counting problem, it's a seeing problem. The model never saw the letters. Before your question reaches the network, a small, separate program chops it into pieces and replaces each piece with a number. The word raspberry, with the space in front of it, is piece number 94,802. One piece. One number. There is no R in 94,802. That program is the tokenizer. It's the first thing that happens to everything you type. It decides how much you pay, how much the model can remember, what it can spell and what it can't, and almost nobody explains.
Every language model has the same front door. Text goes in, and the first stop is the tokenizer. It does one job. It owns a list, the vocabulary, and it cuts your text into pieces that are on the list. Each piece is a token. Each token's position in the list is its ID. That's it. The model downstream never sees text at all. It sees IDs, looks each one up in a table of numbers, we'll get to that table, and does its work. At the other end, the answer comes back as IDs, and the same tokenizer turns them back into text. Encode going in, decode coming out. 2 things to hold on to. First, the tokenizer is not a neural network. It's a list and a procedure, written before the model is trained, frozen forever after. Second, it's lossless. Encode, then decode, and you get back exactly what you typed, to the character. The only question is where the cuts go, and that question turns out to shape everything.
Here's the whole algorithm in one picture. A corpus, 5 words with counts. Cat, 6 times. Cats, 3. Hat, 4. Hats, 2. Chat, 5. Step 1. Split every word into characters. Our starting vocabulary is just the letters A, C, H, S, T. 5 tokens. Step 2. Count every adjacent pair, weighted by how often its word occurs. A followed by T. That pair appears in every word. 6 plus 3 plus 4 plus 2 plus 5. 20. H followed by A. 11. In hat, in hats, and inside chat. C followed by A. 9. T followed by S. 5. C followed by H. 5. Step 3. Take the winner, AT, and merge it everywhere. Every AT becomes one symbol, at. Add at to the vocabulary. 6 tokens now. Step 4. Go back to step 2. That's it. That's byte pair encoding. The only decision left is how many times to loop, and that number, the number of merges, is what sets the size of the vocabulary. GPT-4's vocabulary is 100,000 merges. Ours will be 5. Let's write it.
Run it. Step 1. The table. AT, 20. HA, 11. CA, 9. TS, 5. CH, 5. Merge AT. Every word changes. C at S. H at S. CH at. Step 2. Count again. And notice the table is different now, because the symbols are different. H followed by at, 4, plus 2, plus 5, 11. C followed by at, 9. At followed by S, 5. C followed by H, 5. Merge H at. Now hat is one symbol. In hat, in hats, and inside chat, which is C hat. Step 3. C at, 9. Chat, 5. At, 3. Hats, 2. Merge C at, cat. Step 4. Chat, 5. Cats, 3. Hats, 2. Merge C at,
Chat. Notice what just happened. Chat was built from C plus hat, not from CH plus at, because hat was learned first. The history of the merges decides the pieces. Step 5. Cats, 3. Hats, 2. Merge cats S, cats. And stop. 5 merges, as promised. Our vocabulary: A, C, H, S, T, at, hat, cat, chat, cats. 10 tokens. It never learned hats. 2 occurrences wasn't enough to win a round in 5. Frequency decides everything. The whole vocabulary of GPT-4 is this table, run 100,000 times over a slice of the internet. Nothing else.
Now go back to the opening. How many R's are in Raspberry? The model receives token 94,802. To answer, it has to know how that token is spelled, and nothing in its input tells it. It has to have memorized the spelling of that piece, the way you memorize a phone number, from the places in its training data where the word was spelled out, or rhymed, or split. For strawberry, since 2024, those places are everywhere. It became a running joke, and the joke went into the training data, so strawberry is fine. Here's the honest table from this machine, temperature 0. Llama 3.1 gets strawberry, cranberry, gooseberry, elderberry, and mulberry right, and raspberry, blueberry, and blackberry wrong. Quen 3 gets raspberry right, and mulberry and blackberry wrong. Different models, different memorized spellings, same cause. And the same cause sits under every AI can't spell story, reversing a word, counting its letters, rhymes, anagrams, syllables. The model isn't bad at them, it's blind to them. Modern systems work around it. They write a tiny program or reason step by step until the word is spelled out in pieces. But notice what the workaround is. Spell the word into smaller tokens first. Tokenization was always the problem.